That's the first time. I'm trying not to do what first time I got recorded, I discovered that I was a wanderer. I wandered from one side to the other, back and forth. In those days, the camera didn't track you. So I came into the image and left the image and came back into the image. My kids thought that was the best fun they ever had. So that is the VHS cassette that was in my VCR player for many years. Then we moved and it disappeared. Let's put it that way. However, today I want to talk a little bit about a project that started. I spent a good chunk of my career at Intel, and as a result, I spent a lot of time thinking about high performance processors. But then I left or retired from Intel. I started thinking about other things as well. And one of the interesting things is, of course, IoT is clearly something that comes everywhere. And then all of a sudden, the trade-off isn't as clear anymore. And as Moore's law also goes to an end, it's not at all clear that performance is necessarily the only thing we want to care about. So what we're going to try to do is talk a little bit more about other things. And in particular, I'm going to talk about power. Because IoT is happening. I mean, I think it's perfectly natural to sit in my apartment in Gothenburg and control my robotic lawnmower in my cottage, which is about 300 kilometers away. And I expect that to work. It doesn't always, but it's very neat to be able to sit there and see the lawnmower and see when it decides to go over the edge. That's not so fun, but so far it hasn't broken. However, this is all happening. It's wonderful. It's a lot of neat things happening. But things are not as good. It's becoming the Internet of Things, but it's become the Internet of disasters in many ways. There's a lot of problems with it. Security, privacy, all of these things are happening, which really you really don't want to have to deal with everywhere when everything can do this. A scary one when you can hack the car you're driving and all of a sudden someone take over. That's rather scary, rather uncomfortable for me. So what to do about this and what are the problems? Well, in many ways, there is a lot of low-level programming. Really, if I do only one line here, it would be low-level programming. It's typically written in C. And if they're really advanced, they might go to Rust. That's a major advancement. Still pretty low level. So what we did in a project called Octopi, a bunch of people at Chalmers, we decided that, well, you know, functional programming has done really good work on bigger systems where you wanted to build something that allows high-level programming, where you allow you to compose programs in a reliable way, all the nice things we know about functional programming. However, if you want to do that for IoT device, you have a little problem. And the problem is, of course, that they often run on very, very small devices. They have to run on maybe a battery for 10 years. They might need to run on extreme low power. They only need to be like woken up once in a while. Take a normal state-of-the-art functional language runtime and try to put them on one of those systems. Good luck. It ain't going to work, at least not yet. So the question was, can we maybe do something about this? So the idea was, let's, instead of aim for performance, let's aim for low power, or actually low energy. Power is in some sense not the right word here, because power sort of tells you how much the battery has to be able to provide it in instantaneous time. What you care about is the energy it's using for the computation. So low energy is the key here. So the goal was basically, can we look to design a processor that give priority to energy, security second, clearly we want to deal with that. Try to make it easier to program, make it easier to get it right, avoid a lot of bugs that easily creep in. So, and then only third, and rather distant third, performance. So we said, okay, that sounds easy. I've designed these things before. So a simple graph reduction engine sounds like good. I built a verification system that's been used in Intel for many, many years that actually has a front-end language was a functional programming language. So I had spent my life for many years reading Simon Peyton's book backwards and forwards and so know how graph reduction should be done or not done. So it was familiar to me. So I said, well, that seems simple. Let's try it. And there have been some ideas for this in hardware in the 80s, as you mentioned earlier. But I want to do more. One of the problems when you write IoT devices is this simple things like you typically have 16-bit integers or something like that. You often get overflow. Let's try to avoid those problems. That's a simple one. You often want to have multiple processes. Operating system with multiple processes, shared memory, no memory controller typically. There's a lot of hard difficulty programming there to make sure that you actually have process isolation preferably in hardware. You want to do, if you can, reduce side channels. That was a very big thing for a while. It still is. And we would like to eventually verify it. My background is to do form verification, so of course it had to be thrown in there. I have to embarrassingly say that the one we're going to talk about today has not been verified. So theory and practice, two different things sometimes. Mostly we didn't have the resources to do it yet. And of course, you start small, do something simple. So we did something simple. It looked more or less like this. The right half of this is effectively all the memory. Memory controller, garbage collector, initiation from the ROM into RAM, and so on and so forth, and the allocation mechanism, and so on and so forth. Then you have the graph reduction engine itself. You have a scheduler, I'll talk a little bit more about, and the RLU. So it's at this level, it doesn't look that much different from a normal CPU, except that the graph reduction looks a bit odd. So what is graph reduction all about? Well, I assume most of you know a little bit about functional programming, and it's effectively functional programming is basically sugared lambda calculus. That's the one way of looking at it. And evaluating a lambda expression directly is rather cumbersome. Name capture and things like that make it very difficult to do. So one good way of doing it is compiling it to combinators. It's very cute trick where you can basically make it all applicative. Then you end up with some fixed number of combinators that the whole program is compiled into. So all the named arguments and lambdas, all things disappears. Very nice. You actually need only two, which I think is remarkable. Unfortunately, if you only use 2 S and K, you get very large expressions. So clearly, that's not a good way to do it. The modern version of this is not to use fixed combinators, but using what's called super combinators. Combinators are custom built to the program you wrote. But super combinator, unfortunately, require essentially an interpreter that interprets to build the graph according to when you need to instantiate the graph. That means that you have a normal machine in addition to the graph reduction engine. So the halfway in between is essentially saying, okay, I'm actually going to do a fixed set of combinators, but it's a bigger set than 2. Here's a typical set. If you take the top 10-ish, 9, 10, whatever it is a typical size of fixed combinators. They're sort of, if you look at compilation, you discover that these are kind of useful ones. It turns out that we wanted to have evaluation that didn't use a stack, because stack is sort of on top of other things that makes it complicated. So we'll use, instead of back pointers into the graph, when it does a reduction and traversing down, it uses the back pointer up. And to deal with struct functions, instead of using a stack and reevaluate, so the argument need to be evaluated before you call the strict function, you essentially change the reduction order. So you reduce the constants before you reduce the operations. The trick that reducer on was the one that introduced that idea. Very clever trick, I have to say. It turns out, though, that if you do that, your graphs don't look quite the same as they used to do before that. So it turns out that there is one particular family of combinators, what I call the L combinators, turns out to be extremely useful. A very, very common thing that shows up, and it makes a big difference. So we actually don't have a fixed set of combinators. We have an infinite set, but it's cheating. It's really a fixed set. L is just the parameterized CS as well. C is not as useful, turn out. I thought it was clever, but that was wrong. However, as an interesting observation here, you see the number of combinators. If we go from a fixed set, the ones that had on the previous slide, to the extended one, including the L and C, you see a drastic reduction in number of combinators and the size of the program, if you like, the size of the ROM image. It basically goes factor 2. So that's definitely worthwhile doing. To give you an idea here how it actually happens, if you start here, well, sorry, I'll come in 2 seconds. My next slide isn't what I thought it was. So the important point is that the graph represents both the program and data. So there is no separate program and a separate data. It's all in the graph. And now everything happens in the graph reduction. To make it easy for a memory controller, every graph node is the same size. So we have a fair amount of internal fragmentation, a lot of wasted space, if you like, but it makes it easier and makes it easier for garbage collector and so on and so forth. So it was worthwhile that we felt. Memories is pretty cheap, relatively speaking, nowadays, even for IoT devices. The back pointer I also mentioned, and there's one interesting side effect of using back pointers is that you effectively have 2 pointers to the root of the whole graph and where you currently are reducing. Those are two things that you need to know in order to start evaluating. That means that if you want to switch context now, all of a sudden, you just need to change those 2 pointers, which is basically you can do a context switch from one process to another in basically 2 cycles. An incredibly fast context switch. And furthermore, that means the whole memory image, there's no stack, there's nothing else that gets switched over. So we have extremely low latency context switch. And that's a nice trade-off. There is some payoff, the expense, of course, of this. We have a back pointer in all the nodes, that's extra waste. And there's another point we're going to come to towards the end when we have some results that tells you that this might not be a great trade-off in the end, but we'll see. I said that. Here's the example. Power of 2, so 2 to the 16. It's a rather trivial example, but it fits on the slides. Here's a lambda expression that comes out. So what we actually use is we use the functional programming environment, VOS2, that was part of the system that I used in, as I mentioned, in Intel. I was not able to take the code from Intel, but I was able to take the code that I brought into Intel and from there rebuild it again. So there is a public version of VOS now that is the same, or actually better than the one that Intel has by now. And it has a functional language front end. It does type checking, parsing, type checking, overload resolution, all those kind of things that you need to do. And then it spits out, for our purpose, it spits out the lambda expression. So this is what you come out from when you type in something like that. And it comes up with something like that. It's the reflection features of FL. Then if you do the strictness transformation I mentioned, you get something looking like this. You compile that to combinators, and you get something like this. What's interesting is that the size of these graphs are typically about the same size as the lambda expression. So the combinator doesn't blow up, which is a nice side effect of this one. And then if you run it, here's the snapshot unit reduction. The only reason for taking this is you can see, I don't know if you can see, but there's blue back pointers showing up here. So in the middle, when the machine is operating, it's building these back pointers. At the moment, it's just about to do an L4 reduction. If you follow the spine down here, you will discover the left spine takes you down to L4. And that's going to be the next operation. You can actually see it here. I'm doing L4 in the waveform. That's just going to happen now. So that's just how the machine operates. I'm not going to talk about details, any more details on that. It's fairly straightforward. There is nothing deep or profound here. It's fairly straightforward to design it. It's fairly small, which is good. And furthermore, it's nice that it's effectively, depending on which type of graph it is, that decides what you're going to do with it, which means that each of those can be separate modules that you call. This is important for some reason, for a reason that is going to become clear soon, but it actually allows us to do clock gating effectively. The language we use supports clock gating extensively. So the whole processor is extensively clock gated. So most of the silicon is dark. When you run this, you will have a very, very small part of the silicon that actually is active. The rest is basically dormant. You can actually imagine even doing more extensive clock gating here, where we can actually turn off power entirely to, for instance, the precision unit that only needs to come in when the integers get too big. That may happen very, very rarely. You might even turn off the power to that entirely. The language we use for this is something we invented called Bifrost. And then one major part of that language is that you can have protocols, not just protocol for the communication, like 4-phase handshake or 2-phase handshake or pulse protocol or something like that. It also allows you to have power down protocols and other protocols as well. And you can just switch the protocols on and off by just changing one line. So when we had this processor, we literally speaking changed it from a normal one that ran everywhere all the time to one that's extensively power gated by changing one line. And it reduced the power by about 2/3 directly. So well worth having. It makes it also easier. And in fact, I think in hindsight now, we could write it even better. We can do even more finer grained clock gating here. Would actually make us even lower in the energy consumption, but we'll see how much time we have. The scheduler, let me talk briefly about the instance. I've said most of it already. We provide a process, it's a fixed number of processes, and they basically do round robin preemptive scheduling. And as I said, context switch is almost instantaneous. And furthermore, the communication between them is through email. Well, that would be nice. Mailboxes. However, sending something, the message you send will be fully evaluated, which means that there will be, no matter what you do, there is no sharing. You share the memory, but it cannot change. The memory cannot change. The message is essentially fixed. Even though you can send functions, you can send other things over, but because of them being fully evaluated, you can actually guarantee that memory from this process cannot interfere with memory from that one, and so on and so forth. You get the message, and they can't interact with each other any other way, except through those messages. The memory system, of course, nothing of this makes any sense or works at all if you don't have a good memory system. First of all, the program is a graph. That graph will be reduced. Reduced by definition, it means it's changed. So you can't just have a ROM for the program and some RAM for working the process. You actually have to move the data from the ROM to the RAM before you can run it. So the first thing it does is copy the program from the ROM into the RAM, and then you start the reduction engine. The memory protection I already talked about. There's no side effects between them. The one most important point, though, is of course, it's a functional language. So it generates garbage. You need to be garbage collected. We use a concurrent garbage collector, so it runs in the background, and from the evaluation or graph reduction engine, there is no stop at all. It continues all the time. The cost of that is we double the memory. So it effectively does it by doing a snapshot. Whenever you can garbage collect a snapshot, but what happens is you say the snapshot, and instead of copying everything to the snapshot, you do copy on write. So effectively, first write, I should say. So when you're in a snapshot mode, if you want to write something, it doesn't write to the memory location from the snapshot, it copies to the shadow instead. So effectively, you have a garbage collector that runs completely concurrently. The only thing you notice is that the memory contention is between the garbage collector when you does a mark process or sweep and the general evaluation engine. Currently, they basically give priority to equal to them, but we've actually been discussing of changing that a little bit. So depending how close you are to the edge, in other words, how close you are to running out of memory, you can change the priority to essentially allow the execution engine higher priority until you get close and you say, at this point, the garbage collector has priority. But neither of them stops at any time. They allow you to continue working no matter what until you, of course, unless you run out of memory, then you have to disaster strikes as usual. The arithmetic unit, I sort of mentioned already that we have arbitrary precision. Well, we actually don't. Well, we do and we don't. We have two integer precisions, one fixed, and then when that runs out of, it goes into arbitrary precision. Because the arbitrary precision is effectively a linked list of chunks, but that means that they are half the size. So chunks are small integers, but chained together. So they take some more memory for them, but they can grow, of course, arbitrary size. So we try to live in the single-sized, if it's as long as we can, and because that's fast, that's easy, there's no need garbage collection, and we only go to the arbitrary precision when it needs to. And then, of course, it goes back to integer size if it fits. So it always stays to the smallest possible representation it can get away with. Here's an example of how we write the code, by the way. Small example will be for us. And effectively, it's an imperative language for describing algorithms, and it's compiled into RTL from here. So it's a design language. It's a high-level design language, effectively for arithmetic, not arithmetic, for computational tasks, primarily to computational tasks. When you want to describe an algorithm in an obvious way, you often use because it's very convenient to use. And then, of course, it also has the protocols. It doesn't show up here, but it has all the protocol definitions for how it's going to be used. So that's a very, very quick and very high-level idea of how it looked like. So where are we? So actually, at the moment, we just finished off the second version. We had a first version about a year ago, and it was enough in there. We said, yeah, there's no things here we don't really like. So we decided to actually go, let's do a little bit better. And so we got the second version up and running a couple of weeks ago. It all designed inside the VOS environment, as I already mentioned. And then we compile that into RTL and go through a standard RLS synthesis flow for getting real designs coming out effectively. We have a very simple compiler in place using the front end, as I mentioned. It doesn't do anything fancy at all, and that's probably a big problem at the moment. But we wanted to make sure that we could actually run things first. Run before you run fast is a good idea, I think. So the main things, though, is what do we have? So we did an evaluation. Of course, how are we going to evaluate this? Apples to apples, apples to oranges, apples to watermelons. Well, we tried to do apples to apples. So what we did was we said, okay, Cephalopode uses graph reduction. Do we have, first of all, it's going to run an IoT device, low power, low small design. What can run on that? Well, GHC doesn't, that's for sure. Not even a hope on that. However, we've happened to discover that Leonard Augustin, famous from lots of things here in the functional programming community, had, as a hobby, decided to write a new Haskell compiler called MicroHaskell. And he decided to use fixed combinators, which sounds like, yes, thank you very much. It's also nice to have a really good hacker. His implementation is really good, which is kind of fun to have. We were a bit worried, I have to admit, because I thought, oh shit, he's going to have some really neat tricks here. However, we decided that actually fits nicely on a RISC-V, a small RISC-V aimed for IoT devices. So we have a synthesized RISC-V core that we can synthesize in the same design flow as our Cephalopode process. So we have apples to apples for the designs. We didn't do placement and routing. We just went to RLS synthesis effectively to compare. Yes, it would be different once you do a little bit of place and route, but it probably will not be much difference in terms of they're two different processors, but not one isn't all that much different from the other in terms of performance. At least that's our conjecture at this point. Then we synthesized using a 7 nanometer library using Cadence design tools, since we have available in an academic license agreement. We characterized at 25 degrees. We ran for 100 megahertz clock frequency, so it's not a very fast processor, but the whole point is IoT devices typically don't run at very much higher frequencies than that. It's actually interesting to see that when we did to squeeze them to see how fast they could go, the RISC-V was actually slightly slower than our Cephalopode. The critical path was actually slightly faster on our processor, which actually surprised me because we are doing some rather crappy synthesis at some places. But we weren't aiming for high performance, so that didn't really bother us. So what did we get out of all this? Well, helps if I'm on the right place. Numbers. Let me try to make them a little bit easier. Let's look in relative. So let's make a Cephalopode baseline, number 1. So let's start with looking at the 3 different versions of things. We have Cephalopode, of course. Then we use MicroHaskell, and we call it fixed, because MicroHaskell doesn't have arbitrary precision built in, so to speak. They do have a library, but it's written in Haskell. And the performance of arbitrary precision written in Haskell is not, it's very poor. So effectively, we want to do most of our comparison to the fixed-sized MicroHaskell programs. It is, of course, cheating. It makes it make MicroHaskell look better than it should. So it's cheating, but away from us, we actually are better because we actually are working on arbitrary precision. But the arbitrary precision package in MicroHaskell is so bad, as you can see here, that it's not really interesting. What surprised us more than anything was the number of cycles. We are about 20 times faster than MicroHaskell. That really surprised us. That wasn't the target. It turned out to be that by what we compile to and how we do it, it turns out to be fairly fast. This is particularly surprising, given that we are not pipelined, and the RISC-V core is actually pipelined. It's a 5-state pipeline standard. So that surprised me quite a bit that we got that much better performance out of this one, not what the target was. What's also interesting is that we have very fewer memory accesses. That really shocked us because we expected us to be really bad. We expected to be mostly memory bound all the time. So we actually have lower memory bandwidth. And a part of that, of course, is that the RISC-V needs a lot of memory access just to get the program. It runs a lot of program steps to do one reduction. So it is going to do a lot of reads, mostly reads from the memory, just to know what to do with the graph, interpreted. So that's where this comes in. We actually do it all in hardware. We get the data and we just do the reduction. It's all done in the hardware effectively. And now the important one, though, what this was all about was energy. This is all about. And what we got in the end, we have about 10x lower energy consumption than the micro-Haskell fixed sized and 300 times better than the arbitrary precision micro-Haskell. Of course, don't quote that one. It just looks good. But the 10x reduction for fixed, I think, is real. That's actually an accurate and valid comparison. That's as close to apples as we could get. Now, of course, if I want to be critical, I will say, yes, that's against micro-Haskell that uses fixed combinators, but we know that we shouldn't do that. One should, of course, use GHC style, the spineless, tagless machine, the graph reduction. So we did try to be a little bit honest, at least. So we said, oops, that's not what I wanted. Okay. Do this slide first time. What about, okay, let's dream. Let's assume that we can put GHC's runtime or a pared down version of GHC on this tiny machine. Or we write a new one, do fancy things, whatever it needs to take. Ignore the fact we have multiple processes, ignore the fact that we have maybe arbitrary precision, maybe not. What if we did this? So what we did, we was trying to evaluate our programs on GHC and micro-Haskell. So just to get a ratio of roughly how much better is GHC to micro-Haskell. Just at least to know whether is our advantage simply because, well, if you go to GHC, you will just get it. It turns out that we don't. We get more or less the same if you do up GHC. You use it more or less the same if you fix the arithmetic, and we still get 2x better than GHC of arbitrary precision. And this one, I think we should compare the arbitrary precision because GHC's arbitrary precision is really good. That's a highly tailored C code, if I'm not completely wrong. That's a valid one. And of course, this assumes a lot of magic. So in some sense, I think it's fair enough to say that we're probably pretty good in the end compare this. Now, that is, of course, assuming just we're comparing against the functional language. If we don't do that, if we now just say, well, I'm willing to take the price of writing in C, how much better will it be? It will be embarrassingly better, is my first answer will be on this one. It will also be embarrassingly wrong. That's the other good part of this. However, the interesting thing here is looking at how does it all fit together. I actually don't know how to do a comparison against the whole system when we have the whole operating system and everything else. We actually have to write an operating system in some kind of environment here to allow a real apples to apples comparison. That's going to be hard to do. So if someone has lots of research funding available and want to have a collaboration, here is the place for it. However, it's something that came up that I unfortunately had in my previous slides, and I want to talk a little bit about. One thing, when you look at this in more detail on the energy consumption, you will discover that most of the energy consumption for Cephalopode is not in the where we did all the work in the design, or alternatively taking it, we did such a good job that there's very little energy consumption in the core. Almost all of it sits in the memory. So what it really comes down to, one of the lessons out of this, by the way, this is interesting to compare to if we do that on RISC-V, then it's basically about half in the core. It's much more balanced. We are very unbalanced. Our core is extremely low power, and almost all it comes from memory. But the lessons of this is, of course, well, maybe a trade-off of using a back pointer, something like that, was maybe not that great idea. A back pointer means that every time we traversal down, we traverse down, we read it, then we have to write back the back pointer, then we have to go down and write back. A back pointer is a read, modify, write. So you get 3 memory accesses just to go down the spine. Not a good idea, really, in hindsight. Now, when we know that the memory traffic is what matters. So cephalopod number 3 will probably not do that anymore. So to conclude the talk, I think the nice part is that, yeah, if you aim for really low power, custom hardware is really good idea. It's not bad idea. The nice part also is it doesn't have to be that complicated and all that large. This is not an enormous project. It's not 500 engineers for 5 years. This is 3 students more or less for a couple of years, 4 or 5 years altogether. But that's 2 versions of it. We can get about an order of magnitude reduced energy consumption, which I think is good. We get process isolation, memory safety, and overflow protection all in this one. There's a pretty good message here. If you really want to build IoT devices that you can trust a bit more, this is not a bad way to go down that route. If you also now get lower power or lower energy consumption, that's so much better. It might sell the whole approach. Now, of course, cephalopod, even though this is version 2, we probably need to be version 10 before we really can get good answers of should this be working, should we use this? Because there's so many things we can do. As we have talked about the memory traffic criticality, this is something we would not have known unless we did the build. We built it, measured it, and discovered that that's where it all went. Unfortunately, it takes several years to do this. So it's not easy to do this. This research work is not something you work for 6 months and write a paper about. You work for 3-4 years and then you write a paper and hopefully get accepted eventually. The other thing is, of course, the compiler technology. GHC has lots of tricks in it to make much better compilation techniques. We are not using anything. What can we do there? There's lots of interesting problem here. One can look into getting more out of that. And that's pretty much the end of it. Questions? Yes.
Against the RISC-V rocket, is that with both of them off FPGA?
No, this is ASIC design. So both ASICs. I've not done mapping into an FPGA at all. I have no idea how it would look like. That would be very interesting, actually.
RISC-V rocket in
the biggest problem for FPGA though is that you're going to lose big time in energy.
Yeah,
that's you might gain or be good on performance, but you're going to lose big time on energy because FPGAs uses energy every time, all the time, and they're big, so that's not good. Would be challenging. Maybe. I mean, big enough FPGA, we can put it all on. Yeah.
No, so I mean on an ASIC.
On an ASIC. You probably could. Yes. Yes. Yeah, probably. Yeah. Feel free to do it. The challenging with this one is that it's very easy to say, I should do this, I should do that. We have had many discussions like this in our research group. And then we had to do it. And then we discovered that what we thought were completely wrong. In some sense, that's the best research there is when you don't get what you expect to get. But it's frustrating. And it's a very tedious lot of work you have to do before you get there.
So for me, it wasn't completely clear. The language that you compile is also non-strict? Like
yes, it's a lazy language.
Oh, yeah. Okay. And so any of the programs that you use, so many, just glancing quickly, they don't use laziness, all of them necessarily.
No,
so if you take the most lazy program, how did they compare then?
We have only one actually. We did a Fibonacci, a lazy version of the Fibonacci, and it worked actually very well too. I didn't have it in here. We still have some bug in our compiler, which I wrote. I can't even blame the students for that. And so one of them doesn't we were comparing the two Fibonacci versions, the obvious one and the lazy one. It builds an infinite list of Fibonacci numbers and just picks which one you want to have. Zip with, that kind of version. And one of them crashed the system. So I don't know. What we saw from that was that it actually worked quite well. What didn't turn out to be as good, these L combinators didn't help much. They showed up a couple of places, but they are primarily helpful for strict functions, strict arguments. Because effectively what happens there is the argument needs to be evaluated first, and then a whole bunch of things what you're going to do with it sits on the spine, so to speak. And the L combinator is really, really useful for doing that. Right. So it doesn't really help for lazy functions. That you end up with the normal combinators in the set. Any questions?
Sorry.
No.
Your processor, does it have some sort of caching, or is it just directly going to memory?
Goes straight to memory.
And would there be an advantage of any caching, or is that?
Well, actually, I should. There was. We actually have multiple memories because we have an extra memory for the tags. Because, as I said, we have a garbage collector that is do snapshot, which means that you have some tags on the side that says, "Oh, am I in snapshot mode? And where is my version of the two? Am I currently? Is this the one that I should look for, or is the one to the right of this the one I should look at the moment?" That tag memory is actually cached. So we do rudimentary caching. The thing with graph reduction, and this is something I've been debating many times, is caching really will help very little because it's very poor locality. But that assumes that you have a mark and sweep, the garbage collector. A compactor garbage collector potentially could create much better locality. So there's a funny play here between the garbage collector style of that memory allocation and the caching. It may not be a cache you want. You might actually want to have something a little more intelligent that actually knows what you're doing. You know how the graph reduction goes. You may want to have effectively a stacked cache, if you like, as you're traversing down the spine. Of course, if you do that, you lose the fast context switching. So there's no free lunch. Someone else?
Why do you need a garbage collector at all in this model? You have back pointers, you have just one pointer, so you know immediately if it's getting garbage.
The problem is this is a graph, so it has cycles in it. So you can end up freeing things. You have a cycle sitting dying there, and the cycle cannot be freed ever.
What is with back pointers and cycles?
Well, the back pointer only allows you to instead of having a stack when you traverse down the spine, what you need to do when you do an overwrite of regex is that you effectively disconnect parts of the graph. The garbage collection is the one that has to then find those that have been disconnected, and they can be part of a cycle. So you can disconnect the cycle, and if the cycle sits there, there's no way of recovering it. Now, one thing that would help, what I do in FL, is to have two garbage collectors, having a reference counting garbage collector and a mark and sweep. It turns out that the reference counting works really, really well for a lot of graph reduction in the fixed combinators, and it recovers a good chunk of it. But you still need the other one because of the cycles. But then they only be invoked very, very infrequently. So yeah, there's a whole science clearly about garbage collection, and in particular garbage collection in hardware, which I think no one really has looked at enough. I would love to have more work on this one. This is a rather rudimentary version, so one can play a lot more sophisticated games here.
Okay, we better move on, but thank you very much for that.
Thank you.